So in this video, we're going to come up with a formula for implicitly doing partial differentiation, and then in subsequent videos, we'll show a couple of examples of implementing these formulas. So here's the idea: if I have a function of two variables that's implicitly defined, and it's equal to 0. This is the key. So I have f of xy equals 0, and y itself is some function of x. So in other words, f of xy equals f of x comma f of x. Then here's what we can do based on what we've already learned. If we want to do partial f partial x, we know f is changing because of x and f is changing because of y. So to find out how f is changing because of x, I can do partial f partial x times, I can do dx dx. And then those will go, dx dx is really a 1. So I have the rate of change of f with respect to x really already by doing partial f partial x. But I can multiply by dx dx, which is just another form of 1, plus, now I'm trying to figure out how f is changing because of x, but because y is changing because of x, I'm going to need to multiply partial f partial y times dy dx to figure out how f is changing because of x. So there's a sense in which I could have just written partial f partial x, find out how f is changing directly because of x, and then figure out how f is changing because of y when y is changing as a result of x, and take the sum of those changes. So this, I want to recognize, is just the chain rule that we've been working with in the previous few videos. This is just the chain rule for function f. But there's a couple things that we know. If f of xy is equal to 0, which is the assumption that we're working under, then df dx has to be 0. If the function is constant, then the rate of change of the function has to be 0. If the rate of change of the function isn't 0, then the function can't be a constant. So if f of xy is equal to any constant, then df dx has to be 0. So using that information, we can do a substitution. df dx, because the function f is constant, df dx has to be 0. So I can replace df dx with 0. And we have a more compact notation for writing partial derivatives. We also call this f sub x, and we call this f sub y. So we can simplify the notation by making those two replacements. And look, dx dx is just 1. So let's dump it, right? So what we get is that 0 equals the partial derivative with respect to x plus the partial derivative with respect to y times the rate of change of y with respect to x. And then I can just subtract f of x from both sides and then divide both sides by f sub y to get dy dx by itself. So this is pretty slick. If I want to know how y is changing because of x, if I want to know dx dy, I can find it by taking the opposite of the partial derivative with respect to x divided by the partial derivative with respect to y. And I can extend this idea. So here this slide summarizes what we just did. We just did this, but we can extend the idea that we just did, and the demonstration or proof of it would run out roughly the same way to functions of 3 variables. So if I have a function of 3 variables equaling 0, and z is a function of both x and y, if z itself is a function of both x and y, I can calculate partial z partial x and partial z partial y by taking the opposite of f sub x divided by f sub z, or the opposite of f sub y divided by f sub z. So these are going to be pretty nice shortcuts for us, and we'll see how these work out in the next 2 videos. The next video, I'm going to show an example of this case, which I think is the less interesting case. And then the second video, I'm going to show how this case can be really useful for us when we start off with a function z that's been implicitly defined and we need to know partial z partial x or partial z partial y. So the second video will be the more useful of the two, I think.